Welcome to Math 2320, Section 2.2. In this particular section, we're looking at particular kinds of differential equations that can be solved by separation of variables. Now in blue here, two sections of blue, I have some integrals that are solvable using substitution, but occur quite frequently, and you probably should commit them to memory. The integral of sine ax is minus 1 over a cosine ax. Cosine ax goes to 1 over a sine ax. And the integral of e to the ax, I again pick up a 1 over a e to the ax. And again, all of these are done by using substitution, letting u equal ax. Alright, so in our very first equation here, the idea is to treat the derivative here as a fraction and move around the dy and the dx with the goal of getting all the x stuff together and the y stuff together. So to do that, I'm going to move the dx to the right, and now I'm going to integrate both sides. So I'm integrating 1 dy and I'm integrating the sine of 6x. Well, the right hand side is easy. I get a minus 1 over 6 cosine of 6x. If I integrate 1 dy, this is with respect to y, so I get a y. Now technically, each of these integrals would give me one of these constants of integrations, but thinking of it as lumping them all together on one side. And so we get that the solution is y is minus 1/6 cosine of 6x plus c. In question 2, let's see. Alright, question 2, we have dx plus e to the 2x dy is 0. Alright, so step 1, I try to get them on opposite sides. Alright, now I'm going to divide both sides by minus e to the 2x, and we get this relationship. Now the trick here is to realize that 1 over e to the 2x is the same as e to the minus 2x. And now we integrate both sides. So to integrate e to the minus 2x, I pick up a minus 1 over 2, but that's multiplied by that minus, making it positive, plus c, and the integral of 1 again is y. So the main trick is get them on opposite sides, and the small trick here of 1 over e to the 2x is really e to the minus 2x. Question 3. Alright, question 3, let's see. I'm noticing here we got a y part with the dy. The y is stuck in here, so I'm going to again get them on opposite sides. I'm going to divide by y minus 3 squared. And then at that point, everything, all the y's are on one side, x on the other. And so I integrate both sides. The integral of 1 dx, that's pretty easy. That's x plus c. What about this stuff with y? Well, if you let u equal y minus 3, then you're integrating 1 over u squared. But 1 over u squared is the same as u to the minus 2, making it easy to integrate. And so I get minus 1 over y minus 3. I'm going to flip both sides and multiply through by a minus 1. And then moving the 3 to the right hand side, I get that our solution is 3 minus 1 over x plus c. Question 4, we have ds dr equals ks, a growth differential equation. All right, so I again get the ds and the dr on opposite sides. I'm going to divide by s, so I have 1 over s ds is k dr. Integrating both sides, not too hard. The integral of k dr is kr plus c. And the integral of 1 over s is natural log of s in absolute value. Now at that point, the question is, how do we get our hands on s? Well, there are a couple of facts that we need here. One is e to the ln of something gives me this back because e to the x and ln of x are inverse functions. So I take e of both sides. So e to the ln absolute value of s is the absolute value of s. E to the item on the right. Well, the trick here is e to the kr plus c is writable as a product. And then I just collapse this e to the c as a generic constant in the front. To get rid of the absolute value, technically it's s equals plus or minus c e to the kr. But again, I'm going to collapse all of that business into this particular c in the front. So these c's, they're not all the same c. We're just representing whatever that particular constant happens to be. All right, question 5. Question 5 is a little more complicated. So we separate this item. So the dt goes to the right. I divide by p minus p squared, and I'm going to factor out a p. All right, so I get 1 over p times 1 minus p dp is dt. And so now I'm going to integrate both sides. Well, I can use partial fractions to write this in a form that we can integrate it. So it's writable as a over p plus b over 1 minus p. Again, this is from the topic in Calculus 2 of partial fractions. Now, how do I get this a and b? All right, so let's come over here. I multiply everything by this common denominator, giving me a times 1 minus p plus bp is 1. If I let p be 1, then this term is gone, and I get b times 1 is 1, giving me b is 1. If I let p be 0, this term is missing, and I get a is 1. And so that allows me to fill in a and b. Well, the integral of 1 over p is ln absolute value of p. Now this integral, I can let u be 1 minus p. And when I do that and integrate using substitution, I get minus ln absolute value 1 minus p equals t plus c. At that point, we need a property of logs that you might have forgotten, and that is ln of m minus the ln of n is ln of m divided by n. And if we needed it, if this were a plus in between, plus goes back to a product. All right, so this is ln of p over 1 minus p. And again, I use the trick that e to the ln of something gives me that item back. On the right hand side, I split this again, and I'm going to let this e to the c be this c. At the same time, to get rid of the absolute values, it would be plus or minus, but again, that's all absorbed in this c. All right, now how do I get my hands on all these p's? All right, so I'm going to multiply both sides by 1 minus p. If you distribute, you get a c e to the t. I get a c e to the t minus times a negative p, which I'm going to move to the left. And at this point, I'm going to factor out this common p, and then finally divide by 1 plus c e to the t, giving us this particular relationship or solution to this differential equation. All right, question 6. We're going to use separation of variables to solve this initial value problem. All right, so let's see, moving the dt, move the dt, and now I'm going to divide by x squared plus 1. Integrating both sides. All right, integrate the 6, I get 6t plus c. This integral should be recognizable from calculus 2 as the inverse tangent of x. To get our hands on x, I take the tangent of both sides, and now we make use of our initial value, that x at pi over 4 is 1. So let's see, 6 pi over 4 is really 3 pi over 2. So I'm trying to figure out what is the constant that would make this happen. Well, if you look at the graph for the tangent of x, so this is the graph for tangent of x, when is the tangent equal to 1? Well, over the period 0 to pi, tangent is 1 at pi over 4. So the inside part has to equal to pi over 4, allowing us to solve for c, and c is minus 5 pi over 4, giving us our final solution to this differential equation. So again, separation of variables is when I can isolate the variables on opposite sides and perform integrations.